Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Let's continue from where we left in the last class. In this class, we will cover some important ideas like what information we can directly get from the phase diagram, what is tie line, what is lever rule, how to apply them, and get out some useful information from phase diagram. We'll also see one variant to the diagram that we saw in the last class. Last class, it was isomorphous diagram, and today we will see a small variation to that. It's called as diagram with a miscibility gap. So when we say phase information, consider a two-phase material. It has bright and dark phases. Let's call them alpha and beta. What are the information relevant to this? First, the composition. Let's say this is a binary system, A and B, for example, copper and silver. We have to first tell what is the overall composition. Example, let's say 50% of B and 50% of A. Then, what is the temperature this microstructure belongs to? Then what we read from this is two phases are in equilibrium, alpha and beta. So we know the number of phases and the names of phases. Then fraction of each phase. Example, 0.5 white fraction of alpha and 0.5 white fraction of beta. Then individual phase compositions. Example, the alpha phase, the bright phase may have 75% of A and 25% B, whereas the dark phase, the beta phase, has 25% of A and 75% of B. Okay, so these are individual phase compositions. So these are all the information that are relevant to the microstructure predominantly. But how phase diagram is useful in all this? Phase diagram is useful when we have this overall composition in our hand and the temperature. If we have these two, then what we can read from the phase diagram is how many phases and what are those phases and what is the fraction of those phases and the individual compositions of those phases. All this information can come from phase diagram. The ones in the orange color are the possibly the information that we need to know to interact with the phase diagram and get out some information, and these things highlighted in blue are red from the phase diagram. And phase diagram does not provide information on the morphology and defects. So let's see how to do this. Let's see how to extract this information from phase diagram. First one is fairly simple. There is a point here. At that point in this phase diagram, what are the phases? Input is going to be a definition of this single point. That is, what is the overall composition? This composition in the x-axis, and what is the temperature? So this temperature in the y-axis. So what is the output? The phase information. First is the count of phases, how many phases. Now we are seeing that L plus alpha is the region where this white dot lies. So therefore, this is a two-phase region. So what information we get? Phase count, phase names, composition of each phase, and fraction of each phase. So let's see how to read them one by one. First, the phase count. So in this case 1 here, count is two phases, liquid and alpha, L and alpha, and let's say in this case 2, a different point in the phase diagram, the count is only one phase and the name of the phase is L. Let's see how to read the composition of each phase. And for this case 1, first we have to draw the overall composition line like this. Then use something called a tie line. This green line here is called a tie line. It touches both single phase regions, like the limit, the boundary of the liquid phase region is here, the boundary of solid phase region is here. Okay, those are the two phases present in this region, liquid and alpha. So it touches the boundaries of both those single phases. Then drop down from where it intersects the single phase regions. Okay, So these compositions in the x-axis can be read as the composition of phases. Like the tie line touches the alpha region here, and that's where we are dropping it down. This is composition of alpha. So the B content is indicated. So since it's a binary, A content is implicit. And here it touches the liquid region, and from there if we drop it down, we get composition of liquid, which is again percentage of B in liquid. Write down what we have done. In this case 1, draw a tie line. Tie line is drawn when number of phases are more than 1. That is very important. Drop from where it intersects the single phase boundaries and read the compositions of respective single phases. This is what we have done. Now let's look at a point like this, number 2 here. And in this case, individual phase composition is equal to overall composition because it is in a single phase region, liquid. So the overall composition is equal to the phase composition there. Now test your understanding. What is the phase composition at the white dot? Should tie line be used? Pause and think about the answer. Once you are ready with the answers, you play the video and see the answer. It's a single phase region, therefore phase composition is equal to overall composition. So the tie line has no meaning here. Now let's think about a scenario where the overall composition changes. Let's change it from this value to this value. Then what happens to the individual phase compositions? The tie line doesn't move because tie line is for this temperature. In fact, if you change the overall composition up to this and all the way down to this, you don't get any change in the individual phase compositions. As long as tie line remains there, the individual phase compositions do not change. Okay, so when temperature is fixed, composition of phases is fixed and vice versa. This idea will be dealt in more detail when we go to Gibbs phase rule. So now this is easy to see. As long as tie line is there, if you change the overall composition within the tie line composition range, your individual phase compositions are not going to change. So now overall composition is quite a significant one, right? So if the entire alloys or the material in your hand, the composition of that changes. So if that changes and individual phase compositions do not change, what else will change to accommodate for the change we have done in the overall composition? And this is an interesting question. So if the overall composition changes and the phase compositions do not change, then what else will change? What will change is the phase fraction. So let's see how to calculate phase fraction. Again, when number of phases are more than 1, we can calculate the phase fractions. We have to draw the tie line. The entire setup remains like this. But then we have to apply something called a lever rule. Let's see how to apply that. Let's zoom into this area like this. Okay. Let's take the overall composition to be this CB naught, and the composition of alpha is CB alpha here, composition of liquid CB liquid here. Now if you want to know what is the fraction of alpha phase, what you have to do is measure this length of tie line. Okay, then measure the entire length of tie line. So if you want to know alpha phase fraction, you have to see what is the opposite piece of the tie line. So this piece, okay, so length of that piece divided by the overall length of the entire tie line. That's what will be the fraction of alpha phase. So if you want to know this length, what we need to do is subtract CB naught from CBL. So we get this length. Similarly, if you want the entire length, you can subtract CB alpha from CBL, so that we get the entire length. So that's what goes into the formula for fraction of alpha. So composition of liquid minus overall composition divided by the composition of liquid minus composition of alpha. Basically the B contents. Okay. So what if we want fraction of a liquid phase? Okay. We have to measure this length divided by the overall length. So we get this formula. Okay. So if fraction of alpha is k, the fraction of liquid is going to be 1 minus k because there are only two phases here, alpha and liquid. Alright, so this is how you apply the lever rule and figure out phase fractions. Why this works? It's simply the law of conservation of mass. You can take up a small test. Now this is an isomorphous diagram. So this is a copper nickel alloy that we are going to consider. This is an isomorphous system. Okay, we are going to consider one alloy in this. The overall composition of that alloy is 40 mole percent nickel. So you have to identify where this 40 mole percent nickel is, and this is going to be at temperature of 1250 degrees Celsius. Let's say this alloy is heat treated at 1250 degrees Celsius for a long time. Then what will be the phases inside that? What is their composition and phase fractions? This is what you are going to figure out. So you can stop the video, think about the answer, and then you can play and see the answers. So hope you are ready with the answers. What are the phases? So now let's find the answer. The overall composition line, 40% nickel is this line, and 1250 degrees Celsius I am putting as a tie line there. So this is basically in the two phase region, liquid plus alpha. So these are the two compositions. Okay, that you can drop the tie line where it meets the single phase region, so you can drop it and read the compositions. So something around 33% mole, 33 mole percent nickel is in liquid, and 47 mole percent nickel is in alpha. Okay, so phases are liquid plus alpha. The compositions are 33 mole percent nickel and 47 mole percent nickel in liquid and solid respectively. And in the phase fractions, if you see, applying the lever rule, you will be seeing that 0.5 mole fraction approximately is the composition of, is the phase fraction of a liquid. So obviously the alpha phase is going to be the other 0.5. So that's the answer. I hope you got it right. We saw in the previous class about complete solubility in solid state, and we called it miscibility. What is miscibility gap? Miscibility gap is like this: below a certain temperature Tc, single phase alpha is not stable and it becomes two phases, alpha 1 and alpha 2. Right? So below a critical temperature Tc, a miscibility gap occurs. So two phases form, alpha 1 and alpha 2 in solid state. When we say two phases, what are the difference between them in terms of crystal structure and chemical composition? Let's see that. What is the difference in crystal structure? Both are in alpha structure. Example, FCC. Alpha 1 can be FCC1, alpha 2 can be FCC2. Lattice parameter A value may be different, but essentially they have FCC crystal structure. Now what is the difference in chemical composition? Draw tie lines and check. So draw a tie line, you can see that it will drop here and here. So if it drops here, let's call it alpha 1's composition. When it drops here, let's call it alpha 2's composition. So you can see one is going to have low percentage of B, the other one is going to have high percentage of B, right? So we can say that is B lean and B rich phases. So the difference between this and applying tie line in the previous cases is like in the previous cases we read the phase name from thinking that this is touching the boundary of that phase in both sides. So here both sides we have alpha alpha. So how do we call these two phases? Call them alpha 1 and alpha 2. right? So this is miscibility gap. Fine. So yeah, of course, if you want to understand why these things happen, you have to wait for thermodynamics to come. So a practical example of a system with miscibility gap is copper nickel system. In fact, we have shown the same system as an example for miscible systems, but it is only above 400 degrees Celsius. So below 400, you see that there is alpha 1 and alpha 2 phases form. There is this miscibility gap coming. So this is an example for system with a miscibility gap. All right. I hope the lecture is useful. See you in the next class.